So we are going to continue in the sense that now we are going to have the formalism part of it. How we can just find a language to express quantum mechanics in terms of the language of previous chapter. So rather how the notions of joint distributions, marginal distributions, relative conditional distributions, and how relative parts of the subsystem, which were composed of those subsystems, how they are correlated via these distributions. The first part we'll just try to see in terms of language. For example, how we can express them. For example, see mathematically we have formulated ideas of correlation, probability distribution. So we have in quantum mechanics something which you might know, something called Hilbert space. So Hilbert space is normally we talk of infinite dimensional vector space. The point is mathematically we can see it, we can imagine it that way. The point is when we are going to just map or relate those basis states of which are part composed of this infinite dimensional vector space, which is Hilbert space, with some quantum state psi or wave as such. So in that sense, this assumes importance. For example, when we assume that these state of functions, which are just state functions, which are extracted out of certain states, but which have representation in this Hilbert space, they lead to distributions, lead to distributions over eigen values of Hermitian operators. Which are square amplitudes of expansion. So you can say which have mathematical properties of probability distributions. So, which So these state functions which are distributed over some eigenvalues of Hermitian operators. These Hermitian operators have a peculiar property when they operate on act on these eigenstates. They give these eigenvalues, might have be continuous or it might be discrete, which depends. But in some sense, those eigenvalues or eigenstates they have they can be just in certain range of probability distributions. You should be able to what I should say find them, or they should lie in those distributions. So now these probability distributions are in turn subject to our how we a given random variable how we can relate it, whether it's when the distribution is marginal or whether it's conditional in a given joint distribution. So that's the point. So the point is that, for example, in case of simple system, the problem is not there. But once we have a composite system, which is made of more than one subsystem, so it's these relative subsystems whose evolution vis-a-vis the entire system or the part of the system. So it's that evolution that's matters. That's our focus. So this composite subsystem which leads to joint distributions over subsystems quantities. uh, rather than should say independent subsystems. So we are interested in a subsystem, but that subsystem is correlated in some way with the other parts of the subsystem, other subsystems or the system or a whole, as a whole. And in our coming classes, what coming this thing, we are going to see how we can connect composite system states and derive their joint distributions which have various, what I should say, with various possible subsystems which may be having conditional slash marginal distributions. So in that sense, so we are interested in those subsystems which may be possessing a conditional distribution or a marginal subsystem distribution, but that subsystem is in correlation with the other subsystems or the system as a whole. So it's not that the subsystems are not, they are independent in that sense. So we have to see, so in that sense. So we have to see these relative subsystems or state functions which are part of these subsystems, which will give us correctly give us, for example, conditional distributions of all subsystems. But in case of once we take in the very definition of marginal distributions, it's localized. The parameters are somewhat localized. So maybe it's in that sense, the more what I should say, marginal distributions cannot be generally defined by relative state systems. We use something called density matrices for their effective description. So now we can have the properties of what I should say. So if we just have the properties of we can have properties of this. We can have if we want to have notational representation. So if you now go to this Hilbert space and see how we can formalize our discussion here in a mathematical way. For example, in terms of a rather notational representation or a notational convention. So a Hilbert space H with a scalar product psi1, psi2. So a state is a point. A state is a point psi such that psi of psi is 1 And for any linear operator, what I would say, we can define a functional a of psi. This is expectation value a of psi, as this is the expectation value of a. So a of psi can be written as this inner product of a. This is a linear operator. So you can write it expectation value of psi can be written like this. So we can have a class of operators called projection operators. So operator can be written as phi, which is a projection operator. Can be defined as phi of psi is a phi of psi of psi. Sorry, phi. So projection operator is normally an operator. It operates on a state. It gets the state back. So in that sense, we can say for a complete orthonormal, set, phi I and state psi, we define a square amplitude distribution Pi called distribution psi over phi I psi through Pi is phi I. So it's basically, you can see it, this projection operator, the inner product of it twice, it should give us from this phi of psi is equal to phi psi. So phi psi square, so you have inner product of phi, you can expectation value of phi into psi. So you can see it's also phi of psi, phi acting on psi, you do phi back, phi psi, inner product phi psi, that will be phi back. So you can say it, you can write it like this. So in probabilistic representation, the distribution represents probability distributions over the results of measurements with eigenstates phi I performed on state psi, performed in the system with the state psi. So it's basically how we can relate a state, which is an eigenstate, or it's operating on a state on another state. That's it. So maybe this state is a you can say probability distributions on the measurement of the state phi upon a system in the state psi. So measurement of probability distributions of the state phi in the state psi. So this is the point. Now if we have two Hilbert spaces, if we have Now, now if we have two Hilbert species or two Hilbert species H1 and H2, which form a direct product, such that H3 is H1 cross H2, such that we can have H1 can be part of A1 zeta 1 and neta 1, where zeta 1 belongs to H1 and neta 1 belongs to H2. So the product of these in terms of H3 can be written as A1 AI zeta I neta I J BI zeta J neta J. So you can also write it as, since it's inner product of this can be a complex conjugate. So A star B AI Bj can be zeta I zeta J, one even product, and neta I neta J, another inner product. So you can easily see zeta I and neta I are complete orthonormal sets in H1 and H2. So for any pair of operators A and B or A and B in H1 and H2, so there corresponds an operator C is A cross B, and the direct product of A and B in H3 can be defined by the same effect on the elements of zeta I and J of H3, such that you can say, so you can see so we can see if C acts on zeta I and J, this means C, so A cross B, C is A cross B, zeta I and J. Or you can also write as A zeta I, B neta J. Yes. So it's the simplest form, we can write it this way. Now the more important thing is how we can formalize a system which is not a relatively simple system, we can talk of the more important thing, the composite system, which we are interested in. And that composite subsystem, which is basically relative subsystems related to each other, where they are correlated to each other, via some joint probability distributions. For the marginal case, we used density matrix is an appropriate thing, but if it's not a marginal distribution, so we have to see how we can write the composite systems and the relations of these relative subsystems to each other. Such that again, for composite systems, if you have a pair of systems, S1 and S2, which are represented by Hilbert spaces, H1 and H2, then the composite system S is equal to S1 plus S2, such that which has psi of S can be written as zeta I eta J, zeta I eta J, zeta I eta J, you can see it, zeta I eta J, zeta I eta J. So it's the composite subsystem on the left hand side. So it should be equivalent to individually these subsystems which are somehow correlated. And if it's such that Aij and Aij is 1. So it's states, so basically these are two states as zeta I and eta j. So these are operators and so you can say they have this property. So in case what I could say, Pij is basically Aij star Aij, which is a joint probability square amplitude. Psi S Aij, so it's over zeta I eta j. So in the standard probability distributions, this Aij, that it will be a part of some joint probability distributions. That S1 will be found in the state psi2, and S2 will be found in the state neta I. So in a joint probability distribution, we can say in joint distribution, psi s over phi I and phi j with Pij can be given as Pij is probability of phi of I and theta of j is equal to phi I theta j psi of s. So marginal distribution of psi s over phi I and psi of s over phi j. So we have to see in a joint probability distribution, you can write it like this. But for a marginal probability distribution, we will only take psi s, or we can take only one of the two. We are going to take the portion of that thing. We are concentrating on one particular thing. So first we'll write how we can write marginal distributions and how we can write what I should say conditional distributions. So marginal distributions psi s over phi I and psi s over phi g can be probability is pi is probability of phi of I is basically sigma I p of ij is so first we'll write Pij, sorry. So P of Ij can be written as probability of phi of I and theta of j can be written as phi of I theta of j psi of s square. So you have to see this marginal distributions size over phi. So it's this you have to see the product of this phi I. It's actually acting on this whole state psi s. So marginal distribution over psi of s so this is a joint distribution of psi of s over phi of I and phi of j over Pij. So first we'll define joint distribution. Then we can come to the marginal distribution. The marginal distribution now can be psi of s over phi of I and psi of s over phi of g. So probability of phi of I, probability of I is probability of phi of I is sigma Pij is phi of I theta of j psi of s. Okay. And probability of j is basically is phi of I theta of j psi of s. Okay. In the same way, we can go for this the probability of marginal distribution can be written this way. In the same way, the conditional distributions can be it's basically for example P of I for conditional distribution P of I and P of ij, or for example P of g of I is equal to P of phi I, but it's conditional on g, on phi of g. So it's P of ij on P of g. In the same way, P of ij, it's P of, now it's, here it was I, now it's g, phi j conditional. So if it's phi I conditional on phi j, it's phi j conditional on phi of I. So you can have P of ij denominator to be of P of I. So this is conditional, what I should say, distributions as well as marginal distributions, how we are going to write the same. So maybe we'll stop here, and in the next thing, we'll see how we can define conditional expectations of operators. This is conditional distributions as well as marginal distributions. Now we define how we can define conditional expectations as well as marginal expectations, as well as their distributions, corresponding distributions. And then we can go for these relative state functions in the coming class.